What specific problem does the self-search reinforcement learning (SSRL) method aim to solve, particularly in the context of existing RL approaches to LLMs?
The self-search reinforcement learning (SSRL) method aims to address the challenge of effectively utilizing the internal knowledge embedded within large language models (LLMs) for search-based question-answering tasks without relying on external retrieval tools like web search engines. Existing RL approaches, such as Search R1 and Zero Search, often incur high costs due to extensive API calls and multi-turn interactions with real search engines. SSRL enhances the self-search capabilities of LLMs by employing format-based and rule-based rewards, allowing models to autonomously refine their internal knowledge utilization. This method not only reduces dependence on external searches, but also improves performance on various benchmarks, demonstrating that LLMs can act as cost-effective implicit world knowledge providers. Ultimately, SSRL facilitates sim-to-real transfer, enabling skills acquired through self-search to be effectively applied in real-world scenarios.
Can you explain in detail how the self-search reinforcement learning SSRL algorithm works, breaking down its components and steps?
The self-search reinforcement learning SSRL algorithm operates by enabling large language models, LLMs, to autonomously extract and utilize their internal knowledge without relying on external search engines. The core components of SSRL include a policy model that functions as both a reasoning engine and an internal search engine, and a composite reward function that combines format and outcome rewards. The process begins with the model generating search queries based on its internal knowledge, followed by retrieving relevant information from its parameters. The model is trained using the Group Relative Policy Optimization (GRPO) algorithm, which allows it to refine its search capabilities through iterative interactions, enhancing its ability to generate structured reasoning outputs. Additionally, SSRL employs information masking during training to stabilize performance and improve the quality of reasoning trajectories, ultimately leading to superior performance on various benchmarks compared to models that depend on external search methods.
Provide a simple example to illustrate how the SSRL algorithm simulates the search process using the internal knowledge of an LLM. What are the key steps involved?
The self-search reinforcement learning SSRL algorithm simulates the search process by leveraging the internal knowledge of a large language model, LLM, through a structured reasoning framework. The key steps involved include: first, the model generates its initial thoughts within designated tags, such as less than, think, greater than, to articulate its reasoning. Next, when the model identifies missing information, it formulates search queries encapsulated in less than search greater than tags. Subsequently, the model auto-regressively generates relevant information in response to these queries, which is then incorporated within less than information greater than tags. This iterative cycle continues until the model arrives at a final answer, effectively simulating the querying of an external search engine without actually accessing one. This process allows the LLM to utilize its embedded world knowledge to provide answers autonomously, demonstrating the potential of SSRL in enhancing internal knowledge retrieval.
What are the main advantages of using SSRL over traditional search API-based RL models like Search R1 and Zero Search?
The main advantages of using self-search reinforcement learning SSRL over traditional search API-based RL models like Search R1 and Zero Search include enhanced performance, cost-effectiveness, and reduced reliance on external search engines. SSRL allows models to autonomously refine their internal knowledge utilization through format-based and rule-based rewards, leading to superior performance across various benchmarks compared to Search R1 and Zero Search. Additionally, SSRL significantly reduces training costs by eliminating the need for extensive API calls associated with real-time web searches, achieving a 53 times reduction in training time. Furthermore, SSRL models demonstrate robust sim-to-real generalization capabilities, effectively leveraging external knowledge sources when necessary, while primarily relying on their internal knowledge. This approach not only minimizes operational costs, but also enhances the efficiency and scalability of LLM agents in search-driven tasks.
How was the SSRL method validated in your experiments? What benchmarks were used, and which performance metrics were measured?
The self-search reinforcement learning (SSRL) method was validated through extensive experiments across 7 benchmarks categorized into 3 types of question-answering tasks: general question answering, natural questions and trivia QA, multi-hop question answering hotpot QA, Musique Bamboogle and 2Wiki multi-hop QA, and vague question answering BrowseComp. The performance of SSRL was primarily measured using the PASIT-K metric, which evaluates the accuracy of the model's responses based on the number of accurate answers generated from multiple samples. Additionally, the experiments compared SSRL's performance against various baselines, including traditional RL-based methods like Search R1 and Zero Search, demonstrating that SSRL consistently outperformed these approaches across the benchmarks. The results indicated that SSRL not only enhanced the self-search capabilities of LLMs, but also served as a cost-effective alternative to external search engines, thereby validating its effectiveness in sim-to-real transfer scenarios.
Discuss the limitations of the SSRL approach as described in the paper. What challenges remain in ensuring effective sim-to-real transfer with real web search?
The self-search reinforcement learning (SSRL) approach, while demonstrating significant improvements in performance, faces limitations primarily related to the fixed nature of the internal knowledge within models, which restricts their adaptability to dynamic real-world environments. The paper highlights that although SSRL achieves strong results on static benchmarks, the inherent knowledge remains static, making it challenging for models to generalize effectively to real-time search settings. Additionally, the findings indicate that SSRL-trained models may over-rely on internal knowledge, leading to difficulties in adapting to real environments, as evidenced by their tendency to complete queries with a single search rather than engaging in a more flexible, iterative search process. Furthermore, the gap between self-generated information and external search results can hinder performance, particularly in complex scenarios like BrowseComp, where the model struggles to leverage external information effectively. These challenges underscore the need for further exploration into enhancing the adaptability of SSRL models for sim-to-real transfer, particularly in integrating external knowledge sources while maintaining performance.